So my name is Matthijs. I work at Accelerated, where I give trainings. I give a lot of trainings on data and DevOps related things in my work time. In my spare time, I really like to dig into things and see how they work and what makes them tick. And Docker is definitely one of them. What I'll do today is I'll share a story with you that's based on some experience from like 7-8 years ago when I was doing my first ML project that actually had to go to production. We recently started using Docker for some Django services, some Flask services. We had them running on VMs, and Docker seemed like a good bet to get this machine learning project in production as well. So, I got some help from some people, and I whipped up the first Docker file. And the simplest Docker file that you could probably build to do this looked something like this. Forgo the version numbers; they're a bit more recent than 7 years ago, of course, but. We just grab a decent base image, Python 3.8. We copy in some requirements files. We install them. We copy the rest of our source code, and like maybe we run some tests or we start an application when we actually starting up. Because this was a data science problem, this was a container that trained a model. Our dependencies looked something like this. We had scikit-learn and pandas to do the actual ML part and the data wrangling part, which of course used NumPy as well and SciPy in the background. Produced some plots, so we needed matplotlib to make sure that we could actually get some nice statistics out of this thing as well. So I this together with the code of the actual model, made a nice commit out of this, submitted it, asked for a review, and this is the answer that I got. This container is massive. There's all this stuff in there that you don't need. We can't actually run this thing as it is now. Whoops, that kind of makes sense. And at this point, you also maybe understand why Docker chose like a massive mammal as their logo, because this thing is 1.7 gigabytes for just a simple Python container. It's insane. And if we go back to the Docker file and we think about that thing again, then it's kind of obvious also why it's so big. There was this line in there that said copy ... And it just grabs our entire project folder and yanks it into the container without really deciding whether that's needed or not. And, I don't know about you, but a typical project folder for me looks something like this. There's a Git folder that stores my Git repository. There's an IDE folder, which has like my settings for my development environment. Maybe there's some local data, some locally trained models, some notebooks that I'm using. There's a virtual env in there that I'm using to test things and install things. And all this stuff got copied into my container. And, a lot of this is actually not needed. So, what should we do here? Well, we're not going to sort of one by one type out everything that we do need to add. Instead, what we do is we add like a dockerignore file to our repo as well. This thing works the same as a git ignore. Essentially, it tells Docker, in this case, don't copy all these files when you're copying into your container image. I typically also use essentially the same thing that I use for my git ignore, except that I also add the git folder to the docker ignore because there's no need for git history in there as well. And when I rebuilt this container, it already started to make a bit more sense, but it was still massive. 1.3 gigabytes, it's not as bad. So I committed this, asked for another review, and that's also the feedback that I got. It's much better, but still a bit on the big side. So let's try to shave off a bit more. Let's use a smaller base image, because if you look at the Docker history of this container that we just built, essentially almost a gigabyte of this size came from this Python 3.8 base image. So step 2 in this journey was using a different base image. And that was very, very straightforward, because there's a slim version of Python 3.8 slim or 3.9 slim, which is based on a different Debian image, Debian Buster Slim, which doesn't install like manual pages and other useful packages that you use on like a normal Debian operating system install, but not in a non-interactive environment like a container. So I rebuilt this thing, and at this point, I kind of started enjoying myself. Like, oh, this dropped down to 490 megabytes. That's quite a big difference. That's pretty cool. So I went back to our operations guy and said, this is fun. This is triggering something in me. This number going down, that's brilliant. So what should I do next? How can I figure out what can I still do? And they said, there's this tool called Dive. And Dive is pretty cool. It allows you to look at your container image that you've built and sort of see what's in there. So, at this point, I thought, this sounds fun. This is a couple of evenings of just digging around and trying things. Let's dive in. So this is what Dive looks like. It's a terminal user interface. You run Dive with an image name, and then you get this after some analysis time. And what we see here on the top left, sort of this area, is essentially all the layers that our Docker image contains. You can scroll through them, and then on the right side, you see the files or the state of the file system at that point in time for that layer. Everything in orange is adjusted. Everything in green is new. So we can sort of see what this layer added. And one of the first things that I noticed was that there is an 80 megabyte cache folder. That seems kind of weird. Also in Matplotlib, there's some tests. All these tests have baseline images. That's also like a couple of megabytes. Then if you dig further, you'll see like there's markdown files, and there's txt files, and there's like pyx files, and all of those things are useful in the context of interactive development, but kind of useless for this production container image setting. So I thought, let's just try to get rid of them. So I adjusted my Docker file slightly again, and I added a couple of statements near the end to say, well, get rid of this pip cache, look in this site packages folder and find everything that ends with like JPEG or JavaScript maps or uncompiled C source code. Just get rid of it. That should save, well, at least the 80 megabytes of our pip cache, but probably even more. Now, when I actually tried to build this, I kind of got surprised, because in contrast to what I believed, this actually made our image bigger rather than smaller. It added like 14 megabytes for some reason. And I tried to look around for a bit, but I didn't really understand why this was happening. So back to our operations person. Okay, what's actually going on here? Do you understand this? And he pointed me in the right direction and said, you should read up on how these layers of container images work. Okay, all right, that sounds doable. How do they work? Essentially, when you build a container image, every run statement in your Docker file becomes a new layer. And a layer is the difference in file system content of what happened after the layer versus what was there before. So if you have a layer that adds a requirements.txt, essentially that layer will have a zipped tar file that has that requirements.txt there in that right location. Requirements.txt is not that big. It's like 85 bytes. Just that is that layer that's part of our image. Same thing will happen when we roll pip install. This pip install will run. Docker will check what is the difference after running pip install versus before. Let's take that difference, put it in a tar. That's our new layer as well. Now, the thing that becomes interesting when we start to remove things, because a layer can't go back to previous layers and change things in them. So the only thing that we can do in that layer where we say delete the cache pip folder is essentially make a tombstone. Say that there was a file here, but it's not anymore. From this point on, you should consider it as if it doesn't exist. So it's essentially a 0 bytes layer that says this file that was previously there, treat it as if it's not there anymore. And the same thing happens, of course, for this find thing. This is also why there is no actual size decrease when we structure our container image like we did. So after giving this some thought, the answer was kind of obvious. We need to make sure that we add files and delete files in the same layer. And we can simply do that by chaining some bash commands together. So when I do a pip install, also on the same line, but part of the same run statement, run this find command with the delete. And instruct pip. Pip has an option that says no cache there, so it can actually not even make that pip cache in the first place. And essentially squashing these layers together, oh, that did work. That was quite a big step. One side note, we can do this manually like this, so just combining this adding and deletion in the same run statement. There is also a squash command when you do a Docker build that kind of does this for you, but it just does this for all the layers, which makes it slightly smaller and slightly less work to do, but has some disadvantages with layer caching that are, slightly less optimal that one. So at this point, we shaved more than a gigabyte off our initial image and almost a gigabyte off the image with the dockerignore. So it was going in the right direction. And I started Googling it a bit, and I got some hints that said, well, maybe you should try looking at Alpine. Python 3 Alpine is an even smaller base image than the Python 3.8 Slim version that you're using. And that's true. It's only 6 megabytes or less than 6 megabytes. So that's what I did. I once again changed my Docker file that's built from this other base image instead. Tried to build it, but unfortunately that errored out. Command errored out with exit status 1, Python set up by egg info, check the logs. So I started comparing the log of these two Docker builds, and the first line that looked different was this downloading matplotlib line. On the top, we have the line from the Python 3.8 base image, and the bottom we have it from the Python 3.8 Alpine image. And the main thing that we see different is that in the top here, we see a wheel being downloaded, where in the bottom here, we see a tart.gc downloaded. Right? That seems to be the main difference. And sort of the conclusion here is that PyPI wheels are not compatible with Alpine for some reason. So what is a wheel and why aren't they compatible? A wheel is essentially the reason why most Python packaging just works nowadays. When you do a pip install pandas or scikit-learn, it will just download something, and there's not a lot of dependencies that you need to have pre-installed on your PC. And that's because wheels are a binary distribution format in which all external C code is already built for you, rather than a so-called source distribution, which is the tart.gc thing, in which the C code is not pre-built and actually needs to be compiled on your PC when you install the package. You can see, for example, for pandas, the difference between the source dist build and a wheel dist on the right. In the source dist build, we see algos.c and algos.pxd and algos.pyx, which are the CPython or the Siphon and original C code, whereas on the right we see this CPython 37m darwin.so, this shared object, which is essentially the compiled C code in the wheel distribution for us already. Again, on Alpine, it essentially downloads the left side, whereas on our previous one, it downloaded on Python 3.8, it downloaded the right side distribution. So why are those two things incompatible? And that turns out because Alpine wants to be so small, they use a slightly different set of base packages than, for example, Debian does. This whole wheel thing is brilliant, but there's a lot of work in the background that needed to happen to make this possible. And essentially, all Linux distributions are slightly different from each other. So what the original PEP writers thought of when they came up with the wheel PEP was to make a standard subset of kernel plus user space APIs that we could assume to work on many different types of Linux installations. And they called this standard Many Linux. Part of this standard is that things needs to be built against glibc standard library, whereas Alpine doesn't use glibc as the C library implementation, but uses Moozle. So all normal Many Linux wheels that work on Debian and Ubuntu and what have you don't work on Alpine. So we kind of have to compile the code on our Alpine distribution to make them work. That means adding a lot of dependencies. Build-based, free-type dev, libpng dev for matplotlib, openblast dev for like NumPy and SciPy and stuff. So let's add all of those to our Docker file, install again, do a build, takes about an hour, and it results in a bigger image. That's a bit of a shame. Makes sense though, right? We needed all these build dependencies that we didn't have in our previous Python 3.8 image. So we should probably try to get rid of them. Now we already saw why this doesn't work, why we can't run this a key delete of our build tabs somewhere later on, because that's not how the Docker layering works. But what we also don't want is to squash all these layers together, because with these kinds of build times, like these hour-long build times, we really like to use this Docker layer caching and make the most use out of it, so that our iteration speed is at least somewhat decent. What we can do instead is use this thing called multi-stage builds. Multi-stage builds essentially allow you to have multiple from statements in a single Docker file, and you can copy stuff from an earlier Docker container build in the same file to a later Docker image. So we make a builder stage here in the top, we make a runner stage here in the bottom, and essentially what we do in the runner stage is we download from the builder all the installed packages and all the therefore compiled code as well. We still need open, blast, and free type because those are runtime dependencies. So we add those to the runner image as well. That saves a good chunk of size. But then the last question is kind of, okay, why did we still need open, blast, and free type? Because our wheel has the precompiled code. It runs in the runner image. So why is that still necessary? And open, blast, and free type, by the way, add like 200 plus megabytes to this image. So what makes the wheels that we downloaded from PyPI different than the wheels that we just built ourselves in the builder image? That has to do with that they're still linked against available dependencies on the operating systems dynamically. Those dependencies aren't part of the wheel yet. And we can check this using a tool called Audit Wheel. So Audit Wheel is a tool that can check whether wheels are built correctly, whether they're self-contained, but they can also nicely fix wheels and make sure that they don't need any external dependencies. So this is, for example, a wheel that I built myself for NumPy. I ran Audit Wheel against it, and it says, sure, this looks good, but there's still external shared libraries required by the wheel. If we would do this for Matplotlib, we would see open, blast, and free type in there. But as I said, we can also use Audit Wheel to repair wheels. So if I ask Audit Wheel to repair the NumPy wheel, it will essentially look in the operating system and see, okay, which dependencies, external dependencies did we rely on, and let's copy those into the wheel instead. If we add that to, so if we add Audit Wheel and all those dependencies to our Docker file, install the, or fix the wheels, then copy the fixed wheels to our runner image and run our tests, we see that we got this container image down to 288 megabytes. At this point, most of the size comes from our side packages folder. That's good. 197 megabytes out of the total 230 something, 280 something. But considering we can probably do even better, because we're compiling all the source code anyway, we can ask the C compiler, well, get rid of all kinds of debug information and optimize for disk space. For SciPy, that saves about 10 megabytes. We can add these compiler flags to our pip wheel statements. That saves about 50 megabytes. Then there's one last thing, which we can link some of these system dependencies, these SSO files together using symlinks, and that saves another 50 megabytes. We really shouldn't do this though. This is not normcore anymore. This is not part for a norm conference anymore. We should probably just stick with Python 3.8 Slim and do the decent thing and get Docker images that install in 5 minutes rather than an hour. That's it. Thanks.